All right. So today, the thing I want to sort of get into is sort of our final topic for the semester, which is the integral problem. And we began at the very beginning of the semester, that very first day. If you remember all the way back then, we talked about how calculus is a field of two true problems. Okay, there's the problem of the instantaneous rate of change of things, which is the problem of differentiation. And we've discussed that in actually quite a bit of detail. We've done derivatives, we talked about some applications of derivatives, etc. The other question that is important in calculus is the problem of integration, which is the problem of the area beneath the curve. So integration is the question of area beneath the curve. This is actually a little bit of a it's a little bit of a misleading question. Really, what it should say is it should say the quote signed area between the function and the x-axis. By that, what I mean is that so a signed area basically means that if your area is above the axis, this is a positive area. But any area below the x-axis gives you a negative value. I may have actually actively said during the optimization unit at some point that there's no such thing as a negative area, and there still isn't really such thing as a negative area. But this concept of a signed area is it's just how sort of mathematically things end up working out when we're doing integration. If we want to know the actual total area between the curve and the x-axis, then we would have to do something like an absolute value, which would result in that curve sort of having two different sections both above the x-axis, so positive and positive. So area is a problem that this is a problem that people have sort of studied for a very long time. The area of different geometric objects is something that the Greeks were very interested in. And when our curves represent known geometric objects, then this problem is pretty easy, right? So if we wanted to take the integral here and we wanted to find the area underneath this curve, which just happens to be a straight line, we can break up this curve as a rectangle and a triangle, right? And the triangle has area 1/2 of the base times the height, and the rectangle has area equal to the base times the height. In this case, for both of these, the base is 4 and the height is 2, so is 1/2 of 8, which is 4, and this is just 8. 8 plus 4 is 12. But things get a lot harder to deal with when we have to deal with curves, because there's not really a very nice way to take there's no nice function or geometric formula for what the area underneath a parabola is, for example. So, for example, what is the area under f of x equals x squared plus 1 from x equals 0 to x equals 2?
Can you scroll back up to that graph again? Sorry, my dad kind of butted in for a second there.
I'll provide the PDF of this file in the Discord server afterwards as well. So up here in the right, actually, let me make that a little bigger real quick. So over here on the right hand side, you can see the graph of x squared plus 1. It's a parabola that opens upwards, just the regular parabola, just shifted up by 1, right? Um, and what we're interested in is we're interested in the area of um, that blue region, the blue shaded region there, right? So what is that area? Questions? Sorry.
I got that last part.
Okay. So, does anybody have any ideas how we could find that area? Any suggestions for how we could potentially estimate this? Well, one thing you might do is you might do something like you could count squares actually, right? Like if you were to count all those little squares each and find the area of each of those squares, you could count those up. That's pretty taxing, and it turns out to be something that's actually sort of difficult to do on a very large, like it's difficult to extrapolate out. The method that actually leads to something really nice is what's called a Riemann sum. So the answer is what's called Riemann sums. Or sometimes called Riemann rectangles. Basically, what you're going to do is you're going to take this curve and you're going to draw a bunch of rectangles under it. Right. So you could draw the rectangles under it, or you could draw the rectangles above it. In this case, what I've done is I've taken a bunch of rectangles and I've had the rectangles meet the curve at their left-hand most corner, right? The right hand, or sorry, the bottom of the box is on the x-axis, and the top of the box, the left-hand side of the top of the box hits the curve, right? And those are all rectangles we can find the area of, right? Each of these rectangles has base um, 0.5 units, right? And height um, the height is slightly different based on each one. In this case, 1, 1.25, 2, and 3.25, respectively. So we can find an estimate for our area as zero 0.5 times 1 plus 0.5 times 1.25 plus 0.5 times 2 plus 0.5 times 3.25. We can actually factor out the 0.5 and just add it up and then multiply by the 1/2 afterwards. And that gives us an area of what, 7.5 times a half, so 3.25. Though this is clearly no, sorry, 3.75. Um, though 3.75 is an underestimate. Clearly, the sum of the areas of all of those rectangles is significantly smaller than the area underneath the curve, right? We have all of those blue sections that aren't covered up by a green section, right? The other thing we could do is instead of doing left-hand Riemann sums, we could do right-hand Riemann sums. or right-hand Riemann rectangles. And the predictable difference between a left-hand rectangle and a right-hand rectangle is just that the left-hand rectangle meets the curve on the left side of the rectangle, and the right-hand rectangle meets the curve on the right side of the rectangle. So we can swap those out. And now these orange boxes are right-hand sums, right? So for the right-hand sums, the bases are the same, but the heights are now 1.25, 2, 2, 3.25, and 5. So our total sum will be 0.5 times 1.25 plus 2 plus 3.25 plus 5, which is 0.5 times, that's 4.5, 11.5, right? And that is 6.25, or sorry, 5.75. And this is clearly an overestimate. Right? All of these orange rectangles are above the curve at some point, right? There's those big orange sections that are area that is bigger than what the curve actually is. Okay. So does anybody have any ideas on how we could make our estimates better? Maybe get them to be a little bit closer to accurate?
You could take the average.
You could take the average of them, actually. There's a couple of different ways of doing that. Probably the most geometrically satisfying one is to use trapezoids instead of rectangles. So if we have our curve that's something like this, right? So instead of using rectangles, what if we made the tops of the rectangles into triangles? Wait, what did I just do? I just did something wrong. Hold on. That should actually be here and here. So we could make the top of these into uh, straight lines. And then you get a shape that looks kind of like maybe an old video game, right? It sort of looks curved, but it's not actually curved, right? It's just made up of straight line segments. These are called trapezoidal Riemann sums. Because the shape you get is a trapezoid. It's a quadrilateral with two uneven sides, or rather two parallel sides and two non-parallel sides. However, this approach, while it is quite a bit more accurate than just using rectangles straight up, doesn't really expand ourselves outwards to, like, there's not much more you can do after that. Like, what do you do after you do trapezoids like that? So, can anyone think of another way that we could make this a better estimate? So the other approach that we can use here um, is we can take our same curve, 2, 5, 2, 3.25, 5. And instead of using 4 rectangles, what if we used 8 rectangles? Maybe we'll do right-hand sums here. This is still an overestimate, but it's significantly less of an overestimate, right? Um, our previous right-hand sum looked more like these red lines. So we're closer to what the actual answer is because we've cut out this stuff here, right? So by increasing the number of rectangles increases the accuracy of our estimate. So we could have the width of our rectangles and still follow that same rule, maybe either choose the left-hand side or the right-hand side, right? And have them and have them and have them over and over and over and over again, right? And eventually, if we were to sort of use a limiting process, like the limits we learned about in the very, very beginning of the semester, and we took the limit of this, the sum of these areas as the amount of rectangles goes to infinity, sort of what we're doing is we're sort of getting a more high resolution picture, right? So like a really low resolution picture, like sort of like pixel art in a video game or something like that, it can resemble accurate things. Like it can be sort of an estimate of what actual reality looks like, but the higher resolution your image gets, the higher resolution your textures are or whatever, the better and more accurate those textures become, right? So essentially the idea is that we shrink these rectangles until they have no width at all, and then our estimate becomes exact, right? So essentially what I'm saying there, if we continue to make smaller and smaller um, rectangles, then our estimate will approach the true value of the area beneath the curve. And for thousands of years, this is essentially what integration was. It didn't quite use this term. Riemann actually came around after the fundamental theorem of calculus, and pioneered this specific notation. However, this notion, this idea of sort of estimating areas by taking these smaller and smaller and smaller rectangles, and the fact that they get more accurate the more rectangles you make, this is stuff that was done thousands of years before Newton. These are things that were known for a long time, but it wasn't completely obvious if this related at all to the other subject in calculus. Um, and the thing that links those two questions, so the thing that links differentiation to integration is called the fundamental theorem of calculus. And to get to the fundamental theorem of calculus, we need a little bit of notation. Okay, so let's do some quick notation. the integral from a to b of f of x is the area between, sorry, the signed area between the x-axis and f of x. And we write the integral from a to b of f of x dx. So this integral sign here, it looks like a really big S. Um, it's called the integrand. And it comes from S for sum. We aren't actually doing Riemann sums in full detail in this class. We're not going to be evaluating integrals by limits of Riemann sums. We're just going to jump straight into the shortcut for integrals. But it's good to know where that symbol comes from. And A and B are referred to as the bounds of integration. These are x values. They tell you sort of what's the left side and what's the right side of the area you're taking a look at. It doesn't necessarily, or these, you need to have bounds on this region in order to get an area that makes sense. These bounds can be infinite. We're not going to deal with that very much. And then the dx part here, this is what's called a differential. The idea is basically that what we're doing is we're taking the sum of all those tiny, 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 tiny little rectangles, okay? And that's what the S stands for. It stands for the sum, right? And the height of the rectangles is basically the actual value of the function at a given value of x. And then the width of each rectangle is some tiny, tiny change in x. The way you can think of this, though, is that you have your integral, you have your dx, and then you're integrating everything in between. Okay, they're sort of like parentheses around the integral. Whenever you're writing some sort of integral, you will always start with an integrand. Sometimes it won't have bounds. We'll talk about that in a bit. And you'll always end with a differential. Whatever you're integrating according to, dx, dy, dt, dq, whatever it is, you're going to have a differential in the end. Okay? Any questions about notation? All right. So back to the fundamental theorem of calculus, which I'm going to abbreviate as FTC. There are two parts to the fundamental theorem of calculus. The first part is what really truly relates a derivative to an integral, okay? Which says that if f of x is continuous on a to b, then big F of x, which equals the integral from a to x of f of t dt, is also continuous. And differentiable. On a to b, and and this is the important bit, big F prime of x is equal to little f of x. In other words, the derivative of the integral from x to a of a function is just that function. Integrals and derivatives undo each other. So in layman's terms, the derivative of an integral is the function you started with. So this is actually, in a mathematical sense, this is the truly important part of the fundamental theorem of calculus. This links derivatives and integrals as this semi inverse relation, okay, that a derivative undoes an integral. However, the part of the fundamental theorem of calculus as a calculus student that you'll use all the time is actually part 2. Okay, and the fundamental theorem of calculus actually tells us also how to compute definite integrals. So FTC part 2. And it says, suppose f of x is a continuous function on a to b, and also suppose that big F prime of x is equal to little f of x, then the integral from a to b of little f of x dx, in other words, the area under the curve from a to b of f of x, is equal to big F of x evaluated between a and b, which is equal to big F of b minus big F of a. In other words, if we know a function whose derivative is our original function, then we can evaluate these integrals without ever having to do anything geometric. We don't need to take rectangles. We don't need to do any of that weird stuff. We just need to be able to find what's called the antiderivative. Okay? So the easiest, that's not even close to being how you spell easiest, method to find an integral is by finding the antiderivative. That is to reverse the derivative process. Okay. Unfortunately, this isn't quite as easy as it sounds. Reversing derivatives is a lot harder than finding derivatives in the first place. In fact, it makes it a much more difficult, just a more difficult problem. So what that means for us is that the functions that we're going to be, so technically with the rules you guys know right now for derivatives, you guys can take the derivative of any algebraic function that doesn't have trig functions in it. We haven't talked about how to do trig functions, but any polynomial, any rational function, anything with logarithms involved, you can do all of those derivatives. Okay, basically every function you've ever seen in the math class outside of trigonometry, you know how to take the derivative of that function. However, there will be lots and lots and lots of functions that you've seen before that you will not be able to take an antiderivative. Okay, so if f of x is equal to, let's say, 3x squared, what is an antiderivative of f? So what function could we take the derivative of to get 3x squared?
X to the third.
Yeah, x cubed, right? So if big F of x equals x cubed, then big F prime of x is equal to 3x squared. So the antiderivative of 3x squared is x cubed. So I shouldn't say the, I should say an antiderivative. Okay? I say an antiderivative because this is not the only possible function, right? Can anybody think of another function that when you take its derivative you get x cubed? Don't try to think about some big sweeping change. It turns out that the thing you can do here to make this different is actually a really stupid little technicality. What's the derivative of 6?
0.
0. So what's the derivative of, what if big F of x is equal to x cubed plus 6? Well, when we take its derivative, we get f prime of x is equal to 3x squared, right? The 6 just disappears. So really, we could add any constant. If big F of x was equal to x cubed plus pi, or big F of x was equal to x cubed plus e to the 17th, right? All of these would still bring us to 3x squared after we take its derivative. Okay? So, antiderivatives, when we refer to antiderivatives, there is a distinction between the antiderivative and an antiderivative. So an antiderivative of 3x squared is x cubed. The antiderivative of 3x squared is x cubed plus some constant. So x cubed plus c, where c is a constant. Okay, so when we refer to an antiderivative, we're referring to any function that when we take its derivative, we get back the function we started with. When we refer to the antiderivative, we need to refer to the entire family of functions. Okay. So additionally, if you see an integral without bounds, it refers to the antiderivative and must always have a plus c at the end. So, for example, the integral with no bounds of 3x squared dx is equal to x cubed plus c. Okay. So whenever you see an integral without bounds, it's called an indefinite integral. And the solution is going to be some function plus a constant. Okay? If you see bounds on your integral, then it's called a definite integral. It definitely has an answer. Okay? And a definite integral will have an answer that's a number. It might be a weird number, but you should always be able to give a number as an answer to a definite integral, unless the bounds are variables, which we won't be messing with very much. Okay? So there are a handful of rules for integrals that are very, very nice and behave very much the same way that, or there are some rules for antiderivatives anyways that behave the same way that derivative rules do. So let's say properties of indefinite integrals. So if you take the integral of some function plus another function, like if you have two functions added together, then that's just the integral of the first function plus the integral of the second function. This was a property we had for derivatives as well, right? So if you have an integral of, this is true for subtraction as well, so we'll just put a plus or minus on there. And additionally, the integral of some constant times a function is just equal to the constant times the integral of that function. So in particular, what this means is that if we're taking the antiderivative, or if we're taking the integral of 1/3 times 3x squared dx, that's equal to 1/3 times the integral of 3x squared dx, which is equal to x cubed, sorry, 1/3 of x cubed plus a constant. Technically, we also have to multiply the constant by 1/3, but it was already a constant. If you take some number like pi and you multiply it by 1/3, it becomes pi over 3, which is still just a number, right? So we can absorb that into the constant without any troubles. Question? The antiderivative of x to the n dx is going to be equal to 1 over n plus 1, or sorry, 1 over n, yeah, n plus 1 times x to the n plus 1 plus a constant. So remember that the derivative of x to the n was n times x to the n minus 1, right? So what you did is you multiplied by the old power and then dropped the power by 1. Okay, so multiply, then decrease. The antiderivative does that process exactly backward. So first, instead of So when take the derivative, you multiply, then decrease by 1. To take the integral, you'll increase by 1 and then divide. Okay, so the derivative is multiplying by the old and decreasing by 1. The antiderivative is increase by 1, then divide by the new number. So for example, the integral of x to the fourth plus 3x minus 9 dx is equal to x to the fifth divided by 5 plus 3x squared divided by 2 minus 9x plus a constant. Okay. X to the fourth turned into 1 over 4 plus 1 to the power of 4 plus 1. 3x turned into 3 times 1 over 2 x to the 1 plus 1. That 2 is still 1 plus 1, right? And 9x, that really had an x to the power of 0 on it, right? So the power went up by 1, and then we divided by 1. So 9x. So there is something to be careful with here. What is the integral of 1 over x dx? Well, that's a problem, because we want to rewrite that as the integral of x to the negative 1 dx, right? And then we'll apply our power rule for integrals. We'll say this is equal to negative 1 plus 1 is 0, right? And then we'll divide by 0. And this feels bad. So our power rule for integrals only works if x is not equal to, if n is not equal to 0. Or if n is equal to negative 1. Whoops. Cool. So instead, recall that the derivative of ln of x was equal to 1 over x. So the integral of 1 over x dx is actually equal to the natural log of the absolute value of x. There's a couple of other nice integral rules that we need. For example, what is the integral of e to the x? What do you guys think an antiderivative for e to the x is?
E to the x.
Yeah, because the derivative of e to the x was e to the x. So the antiderivative of e to the x should also just be e to the x. Note that the antiderivative of e to the ax plus b where a and b are constants, is actually going to end up, so this should be a plus c. I'm dumb, I just broke my own rule. This will be a plus c as well. Will actually be, so instead of multiplying by the derivative of the stuff, we're kind of dividing by the derivative of the stuff. You end up with e to the ax plus b divided by a plus a constant. This one doesn't come up that often, the expanded version of the e to the x rule, but just be aware that it is something that may show up from time to time. To me, this is an application of something called U substitution, which we may have time to get to in this class and we may not. But nevertheless, that's there. And that's about all that we're going to get for antiderivative properties for this class, actually. This basically lets you take care of all polynomial functions, exponential functions, and logarithmic functions, as well as like radicals and stuff. One of the big problems with integration, one of the things that makes it a lot harder than differentiation, is that there is no product rule, quotient rule, or chain rule. Okay, there is something that sort of resembles the product rule, but it's not perfect. And there is something that sort of resembles the chain rule, but it's not perfect. And there's not really anything that resembles the quotient rule. We're not going to talk about any of those techniques because they're pretty in depth, right? We're mostly just going to deal with the baseline stuff, right? So the last thing I want to do real quick before giving you guys some practice problems to work on is to do a quick definite integral using the fundamental theorem of calculus. So let's take that last one we did. Let's take the integral of x to the fourth plus 3x minus 9 dx. And let's go ahead and evaluate that between 0 and, for fun, let's do 2. Okay. So what we're looking at here is we're trying to find the area beneath the curve of this function. Okay. So if we wanted to, we could graph that, right? Our function is x to the fourth plus 3x minus 9. And our graph's actually going to be a little bit weird. I should have done this just on a new thing. Let's see here. So we're going between, let's see, let's go -1 to 3. And then let's do 50. So here's the graph of our function over here on the right, right? And we're looking for the area of, so it looks like something like this. And we're looking for this area here minus this area here, right? This area will be positive, and this area will be negative. But we can do this without ever thinking about the graph. We can just find an antiderivative and then plug in our bounds using the fundamental theorem of calculus, right? So the first thing we want to do, so the integral from 0 to 2 of x to the fourth plus 3x minus 9, we want to find the antiderivative, which we did for our previous problem. That's x to the fifth over 5 plus 3x squared over 2 minus 9x. And the nice thing about evaluating integrals is that the fundamental theorem of calculus part 2 doesn't say the antiderivative, it says an antiderivative. Okay, it can be any function that when we take the derivative of, we get the original function. So we don't need to pick one that has a constant. And then we're going to evaluate that between 0 and 2. All right. And to do that, we're just going to plug in 2 and then plug in 0 and take their difference. All right. So that's 2 to the 5 over 5 plus 3 times 2 squared over 2 minus 9 times 2 minus 0 to the 5th over 5 plus 3 times 0 squared over 2 minus 9 times 0. So 2 to the 5th over 5 is 32 over 5. Plus 3 times 2 squared over 2 is just 6. Minus 18. And this whole thing ends up being 0. So we end up with 32 over 5 minus 12, which is 32 over 5 minus 60 over 5, which is 28 over 5. Sorry, negative 28 over 5, which is about, what, negative 5.6. That's not about, that's actually exact. And that should make some sense, right? If we sort of look at the regions here, this little triangle of a region between our 0 and 2 here at 1.465 and 2, this triangle is significantly smaller than this triangle over here, right? This area here is smaller than this area. So we should get a negative answer since the negative area should have this one. And finally, to cap this off, let's actually go back to that very first question, the area beneath the curve from 0 to 2 of x squared plus 1. We now know that we can write this as an integral. We can write that as the integral from 0 to 2 of x squared plus 1 dx. And we can use the fundamental theorem to find this value, right? It's the integral from 0 to 2 of x squared plus 2. So that's going to be x cubed over 3 plus x evaluated between 0 and 2, which is 2 cubed over 3 plus 2 minus 0 cubed over 3 plus 0, which is 8 over 3 plus 2, which is 14 over 3, or 4.67-ish. Right? And if we go all the way back to our beginning discussion of antiderivatives, if we talk about, if we look at this here, our first approximation, the underestimate was 3.75, and our overestimate was 5.75. Exactly halfway between those two ends up being, I think, 4.75. And our actual value ended up being pretty close to that, 4.66667, right? So there's the actual area beneath that original curve. It's 4.67. So it's a fair amount of information, and I think I'm going to cut off the lecture here. Does anybody have any questions before I give you guys some practice to work on? So I have a handful of integration practice problems that are pretty straightforward. I'm going to throw them into chat now. These ones are pretty easy, and if you have any questions and you want some answers or solutions for any of them, feel free to ask me. A couple of them are a tiny little bit tricky, but you're going to use sort of the same techniques that we did for differentiation, right? So remember, for example, that the square root of x is x to the power of 1/2, that 1 over x squared is x to the -2, and you should be okay. The last the last 5 problems, or 4 problems, are, no, 5 problems, are definite integrals. So you should have a final answer, okay, like a number. And the first 6 problems are indefinite integrals. So you should have something plus a c at the end. Okay? So with that, I will let you guys go. I will be hanging out in voice 1 for the next 53 minutes or so. So you can feel free to ask any questions that you have, or check anything out. Please make sure that you go ahead and get those projects in as soon as possible, those surveys. So if you have your data and you have it written up, please get that turned in ASAP. If you don't, please try and make sure you get that done before next class. Okay. And otherwise, I will let you guys go.